So now we're going to go on to talk about intermolecular forces. So intermolecular forces, we have three main types. And so intermolecular forces are basically just any forces that are existing between molecules that hold them closely together and maintain a strength and structure. So intermolecular forces are really important because otherwise, without them, everything around us would just completely fall apart. And so with our intermolecular forces, they're basically the forces that hold all molecules together and provide them with a great deal of structure. So consider like the chair that you're sitting on. Without intermolecular forces, it would just be a whole bunch of separate atoms and it basically wouldn't be a solid. But what intermolecular forces do is they attract all of those atoms towards each other due to differences in charges and temporary and permanent dipoles, and that holds those atoms together at various different strengths to create molecules that stick together to then create materials and structures. And so then that results in our different states, so the solid, liquid, and gaseous states, because we would know that in a gaseous state, obviously they're going to be a lot less attracted to each other, so they're all just bouncing around as a gas. In our liquid state, they're somewhat attracted to each other and they're able to stay reasonably fluid because they're not overall very compacted. And then in the solid state, they are all very well compacted together. And so this is providing that solid structure. And so our three main types of dispersion forces which we need to talk about is, our three main types of intermolecular forces which we need to talk about is dispersion forces, dipole-dipole forces, and hydrogen bonds. And so it's really important to note that these are molecules having interactions between each other. They're not actually bonds like as such which we see within a molecule itself. So these are only temporary and they can be broken, unlike with our molecules, it's much harder to break apart a molecule. And so we can consider that these can be broken in order to boil off certain samples and things like that. So our first one, which is our weakest one, is the dispersion forces. And so these occur between all molecules, and so that includes non-polar molecules. So often a lot of the types of intermolecular forces are going to require polarity or at least some difference in electronegativity due to dipoles in order to have that attraction between the molecules. But with dispersion forces, these will occur between all molecules regardless of their polarity. And so this is the weakest type of intermolecular force because obviously if there's no difference in polarity to cause that attraction between the molecules, there's not going to be that partial positive, partial negative to an extreme extent, which is going to cause an attraction. And so hence it's going to be a lot more of a weak attraction between them. And so there's going to be constant changing distribution of electrons within the molecular electron cloud. And so that's what results in these dispersion forces, because the constant movement of the electrons around them means that there's temporarily always going to be negative and positive parts of the molecule which are changing. And so that means that other positive and negative parts of other molecules which are changing are able to be attracted to those other molecules. And so there's a temporary dipole, but this can obviously be separated quite easily, which is why it's the weakest type. And so this momentary uneven distribution causes uneven distribution in adjacent molecules. And so this differing charge is then what's going to cause that electrostatic attraction. and hence that temporary dipole. And then the larger the molecule is, the greater the strength of the dispersion forces will be. So that's really important to note, is that the bigger a molecule becomes, the more dispersion forces it will have. And so that's something really, really important to remember, because they bring that up in the exam a lot, but also it's just something general that's good to understand about molecules, is that as they get bigger, intermolecular forces will typically increase as well. And so their properties will become stronger, they can build stronger materials, and that's because there are more electrons present in each individual molecule, and so more electrons means more partial negative can be formed, which means that more partial positive can be formed, which means that there can then be more attraction of that partial negative to that partial positive in that temporary dipole. Our next one is our dipole-dipole forces. And so these will only occur between polar molecules. They're the second weakest type of intermolecular force, but they're still reasonably strong. And so these occur when there's a constant uneven distribution between electronegative atoms in a polar covalent bond. And so this causes an electrostatic attraction between the adjacent molecules. And so this is because this temporary dipole, which we were talking about before, is no longer there, or it's still there to an extent, but then we've also got this permanent dipole where we've got part of the molecule is permanently more attracts more electrons towards it, such as in chloromethane. We have this temporary attraction of electrons towards the chlorine, because chlorine is more electronegative than the carbon, and so it's going to pull the electrons towards it more, resulting in the carbon having more protons towards it and the chlorine having more electrons towards it. And so that means that the chlorine of one chloromethane molecule is going to be attracted to the carbons, the partially positive carbons of the neighboring chloromethane molecules. And so that then provides that attraction due to that constant uneven electron distribution and that permanent dipole which is being formed. And so these dipoles, these permanent and temporary dipoles, the temporary dipoles are not represented with a symbol unless it's specifically stated to show that there's a temporary dipole being formed at any point in time. But a permanent dipole, when showing attractions between molecules, is represented by this symbol with the positive or the negative. And so it's showing that we've got a positive where our protons are centered and a negative where our electrons are being centered. Finally, our strongest of the intermolecular forces is what we call our hydrogen bonds. And so it's important to not get these confused and think that they are a bond, because although they are called hydrogen bonds, they are still an intermolecular force. So then there's no actual bonding that has been formed, it's still just an attraction between molecules. However, it's very strong, and so that's why it gets called a bond. And so it is the strongest of the covalent intermolecular forces when we're not considering ionic attractions. And it's a permanent interaction between the most highly electronegative atoms and a hydrogen that is bonded covalently to a very electronegative atom. So that very electronegative atom being oxygen, nitrogen, fluorine, or sulfur. And so when you have this hydrogen bonded to one of these atoms, it means that there's this very, very large difference in electronegativity, which then results in this permanent dipole being formed. But not only is it just a permanent dipole, it's an extremely strong permanent dipole. So for example, in a water molecule, the oxygen is going to be a lot more electronegative than the hydrogen, and so there's going to be a lot more attraction of the electrons towards the oxygen than towards the hydrogens. And so that means that the oxygen part of each water molecule is going to be very, very negative and is going to have lots of electrons attracted to it, whilst the hydrogen part of the molecule is going to be very, very positive and going to have a lot of protons attracted to it. And so this means that there's electrostatic attraction because there's local uneven electron distribution. And so what this means is that the local even electron distribution means that the very, very positive part, where the hydrogens are, can be attracted to neighboring water molecules on the oxygen, so on the very, very negative part where the oxygen is. And so this allows these molecules to be attracted to each other, thus forming the hydrogen bonds. And so molecules can often have multiple different intermolecular forces. So a molecule with hydrogen bonds typically also has dipole-dipole interactions and will always have dispersion forces. So we remember that every molecule is always going to have dispersion forces. It's just whether it also has dipole-dipole interactions and hydrogen bonds too, or whether dispersion forces are the extent of its intermolecular forces. We also want to consider larger molecules because they are going to have greater dispersion forces. And so this effect is often going to be insignificant though when we compare the effects of additional hydrogen bonds or dipoles. And so this is because although a molecule such as ethane is going to have fairly low intermolecular forces, then when we go up to something like octane, that's going to have a lot greater intermolecular forces because it's got greater dispersion forces. However, if we're comparing something like octane with something like ethanol, we know ethanol has a hydroxyl group. A hydroxyl group is an oxygen bonded to a hydrogen. And so remember that oxygen bonding to hydrogen causes a hydrogen bonding. And so hydrogen bonding is going to be so much stronger than considering a large alkane type molecule like octane. And so although octane is going to have strong dispersion forces because it's a large molecule, something like ethanol with hydrogen bonds, although it's only very small, will have a lot stronger intermolecular forces because its extent of intermolecular forces with the hydrogen bonding is a lot greater than the extent of strength of a dispersion force. And so the overall strength of these intermolecular forces is going to determine the molecule's physical properties. And so these physical properties are going to include melting point, boiling point, vapor pressure, and solubility. So with melting point, as the intermolecular force strength increases, there'll be greater melting point. And so this is because in order to melt a molecule, you have to separate the intermolecular forces between the individual molecules. And so this is then what allows it to go from solid. You then separate all those intermolecular forces and the molecules are able to spread out, thus melting. And then they go on from being melting and being a liquid to then being boiled if you continue heating them. And so boiling will also require the remaining intermolecular forces in the melted state to then be separated further so that it can then be turned into a gas. And so this is because we are applying heat energy to these particular substances in order to break the intermolecular forces. And so the stronger the intermolecular forces are, the more heat energy which needs to be applied to then break those intermolecular forces. And so that's why if there is a stronger intermolecular force, you're going to require more heat in order to melt and then boil that particular substance. We can then consider vapor pressure. So vapor pressure is the likelihood of a molecule to evaporate. And so vapor pressure is inversely correlated with boiling point when we're considering intermolecular forces, because if we consider boiling point is turning something from a liquid to a gas, and vapor pressure is basically the same concept. It is how likely we are to evaporate something. And so, basically the opposite, because it's how likely we are to evaporate something. And so in order to evaporate a particular molecule, we separate the intermolecular forces, and so as the intermolecular force strength increases, it's going to be less likely to evaporate because the molecule is going to be less likely to separate due to those strong intermolecular forces, so it's going to be less likely to evaporate away. Our final one is solubility. So solubility is considering how likely our particular substance is to dissolve within another solvent. And so this is considering solubility in water, because with solubility in water is obviously polar, and so we know the concept of like dissolves like. So like dissolves like is going to mean that polar solvents, such as water, will only dissolve polar solutes, and non-polar solvents, such as our alkanes, will only dissolve non-polar solvents as well. And so it's like dissolves like. And so when we consider solubility, we're specifically considering solubility in water. So water being polar, the stronger the intermolecular forces become, the more soluble our molecules are going to be. So we're now going to do some example questions. So again, like we did before, I'll leave you guys a few minutes to try these on your own, and then we'll go through the answers together. So our first question is, why does increasing intermolecular forces affect the physical properties of substances? And then our second question is, what are the intermolecular forces that are acting on H2O, CO2, and NH3? So I'll give you 2 minutes to try those questions on your own, and then we'll talk these through together. Okay, so we'll now go on to the answers. So with our first one, we can see that physical properties are going to be affected by the strength of intermolecular forces. And so melting, boiling, and freezing points are going to increase as the intermolecular forces increase, whilst vapor pressure is going to decrease as the intermolecular forces increase. And then for question 2, so our first one was H2O. So H2O has both dispersion forces and hydrogen bonding. And so this is because we've got that hydrogen bonded to the oxygen, and so that is obviously got a very, very large electronegativity difference. So that results in the hydrogen bonding. And it also will have dispersion forces just because we know every molecule displays dispersion forces. Our second one was CO2. So CO2 does not have a large difference in electronegativity, nor does it have an unequal distribution of electrons because it is a completely symmetrical molecule. And so hence it will only have dispersion forces. Our final one is our NH3. And so NH3 has both dispersion, dipole-dipole, and hydrogen bonding. And so this is because NH3 will display dispersion forces as all molecules display dispersion forces. We know there's definitely hydrogen bonding because we have a nitrogen, which is a highly electronegative atom, bonded to hydrogen. And then we also know that we have a dipole-dipole interaction because we've got that lone pair at the top. And so this is relating back to our VSEPR theory, where we know we've got that lone pair which is repelling the molecule downwards. And so because the molecule is being repelled downwards due to that lone pair, it's forming these temporary, these permanent dipoles when it's being pushed downwards between each of the hydrogen atoms and the nitrogen atom. And so hence we have dispersion forces, dipole-dipole interactions, and hydrogen bondings in NH3. And so another point I want to consider and bring up with these is which one's going to have the strongest intermolecular forces. And so out of CO2, H2O, and NH3, we can see that NH3 has the most number of intermolecular forces. And so it has dispersion, dipole-dipole, and hydrogen bonding. And then when we compare that with water's got dispersion and hydrogen bonding. So that will have a little bit lesser of intermolecular forces, but it won't be as weak as something that is very weak like carbon dioxide. And so we can see carbon dioxide will have the lowest intermolecular forces out of all of these particular molecules. Water will have the next highest, and then ammonia or NH3 will have the absolute highest. And so that's just because of the compounding effect of all of the intermolecular forces adding up.